Welcome back. This is lesson 39 of our Networking Mastery series. And today we're tackling something that runs silently underneath nearly every system you'll ever touch: network time. We're going to look at why every device on your network needs to agree on what now means, and how the Network Time Protocol, NTP, makes that agreement possible. It sounds mundane, but when clocks drift, logins fail, logs lie, and audits fall apart. So here's the path we'll walk together. First, we'll ground ourselves in why time sync actually matters, the real-world fallout on logs, certificates, authentication, and forensic investigations. Then we'll get into the mechanics of NTP itself, the protocol, the packet exchange, and that stratum hierarchy that organizes time sources worldwide. From there, we'll roll up our sleeves and configure NTP on real routers and servers. And finally, we'll close on security, NTS, authentication, and the attacks you need to defend against. Let's start with the why, because this is where it gets real. Picture an incident at 3 in the morning. Server A logs the event at 14:32. Server B says 14:35. Are those the same event or two different ones? Your forensic timeline just collapsed. Kerberos is even less forgiving. Tickets carry a 5-minute validity window, and if your clock drifts past that, AD logins fail and file shares mysteriously drop. Certificates expire against the wrong wall. Distributed databases split brain, and in financial trading, MiFID then demands sub-100 microsecond accuracy. Miss it, and trades get invalidated. Time sync is invisible until it isn't. So now that we know what's at stake, let's meet the protocol that solves it. NTP, the Network Time Protocol, has been quietly running the internet's clocks since 1985, with the current version, NTP v4, standardized in RFC 5905 back in 2010. It rides on UDP port 123, uses a hierarchical request-response model anchored to UTC, and polls adaptively, anywhere from once a minute to once every 17 minutes, depending on how stable your clock looks. Worth knowing its cousins, too. SNTP is the stripped-down version you'll find in IoT gear and cheap routers. No filtering, just ask and accept. And PTP, IEE 1588, is the precision sibling, using hardware timestamps to hit sub-microsecond accuracy. That's what trading floors and telecom networks reach for when milliseconds aren't good enough. Now, how does NTP actually organize all these clocks? Through a hierarchy called stratum, basically a tree measuring how many hops you are from a true reference clock. At the top sits stratum 0, the atomic clocks, GPS receivers, and radio sources that define time itself. Stratum 1 servers plug directly into those. Think time.nist.gov. Stratum 2 syncs from Stratum 1, like pool, ntp.org, or your ISP's NTP. Stratum 3 is usually where your enterprise servers or routers live, handing time down to clients at Stratum 4 and beyond. Each hop adds roughly a millisecond of drift. Stratum 16 means unreachable, and the practical rule is simple. Pick the lowest stratum you can reach reliably. So, once you've picked your stratum, how does the client actually correct its clock? With 4 timestamps. The client stamps T1 when it sends the request. The server stamps T2 when it arrives, and T3 when it replies, and the client stamps T4 when the answer lands. From there, it's grade school algebra. Offset is the average of the two apparent gaps, and delay is the round trip minus the server's processing time. The catch is the assumption that the forward path and the return path take equal time. On asymmetric routes that breaks down, which is why NTP samples repeatedly, throws out the outliers and averages what's left. Now, let's put that theory into a real design. In a 1,000-device network, you don't let every router and workstation reach out to the public internet for time. That's noisy, fragile, and a security headache. Instead, you stand up 2 internal NTP servers, NTP1 and NTP2, and point them at 3 or 4 trusted external sources like time.nist.gov or time.google.com. Everything inside, your core router, your access switches, your app and database servers, your workstations, syncs only to those two internal boxes. Two servers for redundancy, multiple upstreams so no single source can poison your clock. So here's how that internal NTP server actually looks on a Cisco router. You start by setting the time zone and daylight saving rules because the router won't guess them for you. Then you point it upstream at a few public sources. Notice the prefer keyword on time, NIST.gov, which tells the router to favor that peer when they're all healthy. The NTP Master 3 line is the key one. It tells this router to act as a Stratum 3 server for everyone inside. And sourcing from loopback 0 means your clients always see the same IP, even if a physical interface flaps. Finally, show NTP status confirms you're synchronized and tells you exactly which upstream you're locked to. Now that your NTP server is running, here's why you need to lock it down, because if an attacker controls your clock, they effectively own you. Push a client's time forward and suddenly expired certificates look valid and replayed tokens get accepted. Sit in the middle and lie about time or pretend to be a Stratum 1 source on the LAN and you've poisoned every device that trusts you. The classic monolith amplification attack turned NTP servers into 500x DDoS cannons for years. The defenses map 1-to-1. NTS from RFC 8915 wraps NTP in TLS. Symmetric keys authenticate peers. Pulling from 3 or more unrelated sources lets outlier detection catch a liar. Disabling monlist kills the amplification vector. And access lists restrict who can even ask. Now, NTP gets you within a few milliseconds, and for 99% of networks, that's perfectly fine. But some worlds need much tighter sync. High-frequency trading, where microseconds equal millions, 5G radios that have to hand off cleanly, broadcast studios aligning video frames. That's where PTP, the Precision Time Protocol from IEEE 1588, takes over. The trick is hardware timestamps in the NIC instead of software, plus PTP-aware switches acting as boundary clocks that strip out their own latency. The result is sub-microsecond, often nanosecond accuracy, but you pay for it in special hardware and firmware. Rule of thumb, stick with NTP unless your use case specifically demands otherwise. Back in the real world, though, most NTP problems aren't about precision. They're about silent failure. Firewalls quietly drop UDP 123, and clocks drift for weeks before anyone notices. A device showing Stratum 16 means it never actually synced, even though it looks happy. Virtual machines drift minutes per day under host CPU contention, unless you run both the hypervisor integration tools and NTP inside the guest. Log everything in UTC. Local time across regions makes incident correlation nearly impossible. And for leap seconds, use a leap smearing source like Google or Cloudflare. The 2012 and 2017 outages are a reminder that just one extra second has taken down real production systems. So let's pull the whole lesson together into 5 things worth remembering. First, time matters. It's the invisible glue under log correlation, certificates, Kerberos tickets, and compliance audits. Second, NTP runs over UDP123 with a stratum hierarchy from 0 to 15 and 16 meaning unsynced. Third, the offset calculation assumes a symmetric path. When that breaks, so does your accuracy. Fourth, the enterprise pattern is 2 or more internal servers pulling from 3 to 4 external sources with everything else syncing internally. And finally, secure it. Use NTS or authentication keys. Keep multiple sources so one liar gets outvoted, and always filter monlist to avoid being an amplification target. And to make all of that stick, here's your cheat sheet, the one-page reference worth screenshotting before you close the video. NTP RFC 5905, UDP port 123, anchored to UTC with an epoch dating back to 1900. Stratum 0 is the reference clock. 1 is directly attached, 2 through 15 step outward, and 16 means don't trust it. The offset formula assumes path symmetry, and in practice, you're looking at sub-millisecond accuracy on a LAN and tens of milliseconds across the internet. That wraps up time synchronization. Next up in Lesson 40, we shift from keeping the network on time to actually watching what it does. As NMP for polling device health, SysLog for collecting events, and NetFlow for understanding traffic patterns. If this lesson clicked for you, hit subscribe over at youtube.com, Dargslan, and I'll see you in the next one.